Okay, hello everybody. I'm talking about what it says on the screen, but I'm going to jump straight in with some motivation. So basically, there is dust in space everywhere. It's important in how stars are born in star formation regions. It's important in how stars die. We find it in between stars, and it's important for molecule formation and dynamics. And we find it in other galaxies. In fact, as far back as we've managed to look in redshift, we have found dust. And understanding that dust is really important. Now, one of the things that's come up in the last couple of decades is that although in the interstellar medium, the dust seems to be entirely amorphous, and I'll define that in a couple of slides, we found that there's a lot more crystalline material being made by the stars that send dust into the interstellar medium. And so there's this paradox of whether the stuff should be crystalline or amorphous. But before I get into all of that, I want to give you some motivation here. So why is this important? Well, the dust really does impact any environment in which you find it. It's going to impact because chemistry can happen on its surfaces. It's going to have an impact because of how light interacts with it. And the light interaction is really important because that both changes the energy flow through a system, but it also affects the dynamics because the dust will absorb light and take its momentum. And so it affects the motions in a system. Now, here you can see I've got a slide of carbon dust, well, rocks. And the point here is that when we look at carbon, we can arrange those atoms in different ways. So if we have graphite, invisible light, it's absorbing most of the photons that hit it. That's why it's black. But if we look at diamond, it's actually letting most of those visible photons through. So the difference is going to be huge in how it interacts with the light that it comes in contact with. So even though it's made of the same atoms, the crystal structure is crucial. Now, so it's likely that it's mostly amorphous, and then the issue has more to do with the surface and what sort of interactions can happen on the surface. Actually, what's out in space is going to be a mixture of carbon, mostly carbon grains, and silicates. So for carbon, think soot, and for silicates, think sand, but mostly black sand from a volcanic beach. But here what I've got is something that's showing you the different ways those grains could exist. So you could have single crystals where the atoms are all nicely oriented in a simple pattern. And there's a picture of a quartz crystal. I think most people know what quartz looks like. And beneath that, I've got silica glass. So it has exactly the same composition, but now it doesn't have any long range order. The units of silica are randomly oriented relative to each other. That would be an amorphous grain. But then on the other side, you've got what's called polycrystalline grains. So if you've got something that is single crystals, but they agglomerate in random orientations, you get something that instead of being transparent, like the single crystal, is translucent, like the rocks on the, what side is that? Right. And then you could also have things, think about what granite looks like. That's where you've got a mixture of different compositions, okay? So when we're thinking about what we're looking at in space, we think that most of it is like the glassy grains, but a lot of what we're seeing in stars seems to be more crystalline stuff. So what is it that we've done? Well, here, hopefully this will play it's not playing. Okay, I may need some technical help on this one, or we may just have to show it later. What this should be showing you is a video of molten rock cooling. I had it set up so it would automatically play, but I think it's not my friend today. I'm going to let him play. Basically, what this is an image of, it's a crucible that's about 2 inches across. And in it, there is molten rock. The rock is made of a pyroxene silicate. So it's a silicate similar to what we would get in space. And thank you. And hopefully it will replay as well so you can see it. But what's happening is as it cools, crystals are starting to form. So you've got something that is a liquid. It is forming crystals. And when the crystals form, they glow. Anywhere that is yellower and brighter, that is hotter material. Anywhere that is redder is cooler material. And what we see is that the crystals will start to form, and then they'll form out it's like a ripple effect as the crystals are moving out. And so what you see is crystals forming in the middle there, and then you're seeing them get very, very bright. And what's happening is as crystals form, they release energy, and that causes the crystals to heat up. And this is important for understanding what happens with the crystals that we see in space. Oh, but now It won't let me advance. Okay, I'm just going to keep talking. I can do this without slides. Okay, so what's actually happening here is we've actually monitored this. We've actually monitored this for thank you. So here we've got a graph of temperature and time. Don't worry about the bottom line. That's a different composition. These were experiments that were done for geology rather than astronomy. But the top one is an experiment where we're looking at that same composition. And you can see for the first 8 seconds, what you have is the temperature is just cooling. And then about 8 seconds in, there's a spike in the temperature. The sample is spontaneously heating. That's when the crystallization occurs. And if you look at the dashed line, that's where we're focusing in on a small area. So you're really seeing a single crystal growing. And we're seeing a temperature change of 150 degrees. And so this is the thing that we think is probably happening in space. This one is actually showing you the apparent heat capacity as a function of heating and cooling. Now, in these experiments, although for dust formation, we care about a gas that's cooling and then dust is forming, because the way the instrument works that these experiments were done in, the cooling is passive. It just cools at whatever rate it cools at. But the heating is controlled, so we control the rate at which it heats. So that's a better measure. So that's the red in this graph. And where you see there's a big dip and it looks like it has negative heat capacity, that's because it's spontaneously heating up. Essentially what's happening here is this is a measure of how much the instrument has to provide heat to keep the sample heating at a constant rate. And so when it has that dip, that's because it is heating, it's providing its own heat. The instrument no longer has to provide it anything, okay? And that number that you see, the delta H crystal, that's enthalpy, that is actually the amount of energy per gram that is being produced. So you can see that there's a lot of energy being produced by this process. And because the brightness of something is very dependent on the temperature, it actually goes as T to the 4th power. So a small change in temperature has a big change in the brightness, and that's why you saw that big brightening in the video. Okay, so just to summarize what we think is happening, basically, as dust forms around a star, it's going to follow a similar process to the lava cooling in the crucible. If it's at about the right temperature, it's going to form something that's amorphous, but then as it cools, it's going to crystallize. It depends on the precise temperature it forms at. As it crystallizes, it's going to be hotter than the surrounding material. You're going to have some amorphous stuff that is cooler. And so when we estimate how much material there is, we're saying there's a lot more crystalline stuff than there really is, because we're assuming everything's at the same temperature. But actually our crystals are much, much hotter. And so this means that what we think is true for the interstellar medium is probably true for what's being put out there by the stars as well. The crystalline material is not as important as we thought it might be. And why is this important? Well, what the dust is made of affects everything. Thank you.
Okay, I'm going to talk about far infrared polarization of Cassiopeia A. We have very big international collaboration, including University of Texas in Arlington, with graduate students, Arab and Rabi, then collaborators from Belgium, Germany, South Korea, and UK, as you see here. Okay, what is the mystery of dust in the universe? After Big Bang, we have a dark age. Then first the stars born, then stars die. Then huge amount of dust is observed in high redshift galaxies using Herschel and ALMA. So where does that come from? Because what we see, what we know about dust is the well-known dust source is evolved stars. They have not born in early universe. So supernova are good candidates. Theoretical models show they might be able to explain. So here is one example, previous spectral image, that really dust is aligned with ejecta. As you see here, it's not forming dust inside of ejecta. So then why polarization? Because dust really mass depending on cold dust. So previously, really no cold dust exists. That means the mass is too small to explain dust in the early universe. So as you see here, you know, people suggested no dust in associated case A. When polarization, after that, there is more polarization measurement. So we used the SOFIA 2.5 telescope then to map the polarization maps. So what the goal is that we want to see magnetic field flow, what type of dust, and grain size, everything previous speaker talked about, how important the dust is. So then, really supernova is the dust producer in the early universe. So we have an image here in the left, red image, the SOFIA image, and blue is the Spitzer and Herschel image. You can see it's cold dust. That's important because that's contributing dust mass. Here is to the right side, we have a polarization flow here. As you can see here, there are directions here and very well-aligned magnetic field direction, which is this blob corresponding in the left here, southwest eastern shell in here. And west, there is just random things, which that means it's not aligned. So you can see some direction of the magnetic field. Then how dust grains produce polarization? If dust is perfectly spherical, you do not see the polarization. Basically, magnetic field and dust grains, it's almost perpendicular. So when it's really elongated, it makes grain polarized. So here is, we really discover high percent of polarization in Cassiopeia A. This is one of the highest polarization source, typically, less than 7% in interstellar medium and many other objects. Also, the analytical solution we solve indicate this dust only have to be large grains. And also from, as you explained, the silicate over the carbon dust, this, in order to have this high polarization, really silicate dust is needed. More important, really supernova are really, when we just, take the emission from polarized light, we can estimate enough mass to explain the early universe. It's the same order of magnitude from total emission mass. Okay, thank you.
Hello, everyone. Just to introduce myself again, my name is Ivanna Escala. I'm a Carnegie Princeton postdoctoral fellow here at the Carnegie Observatories in Pasadena. So today I'm here to report results from a recent paper by my collaborators and I. So this is a study on a tidal shell around the Andromeda galaxy, which is one of our neighbors here in the local group and is a Milky Way-like galaxy. So we're reporting the spectroscopic confirmation of a tidal shell and evidence, new evidence, I should say, that the system of the brightest tidal features in M31 very likely all originate from the same event. So the reason that we're interested in studying things like tidal shells is because they can tell us about a galaxy's merger history. So galaxies like the Milky Way and Andromeda grow by merging with satellite galaxies. So this is a simulation from the Aquarius simulations that illustrates this process. It's from a while ago, but I think it's a good example where you have these often smaller galactic systems that are coming in and being tidally shredded by the gravitational influence of the host galaxy. So in this case, the host galaxy would be M31. So studying these tidal remnants can tell you about the dark matter distribution of the host galaxy, as well as the properties of the original satellite galaxies that were destroyed in this process. So you may have heard about stellar streams before, which you can see within this image. So these are elongated ribbon-like features. So tidal shells are the same thing in the sense that they're tidal debris, but the difference is that they appear as shelf-like features on the sky that are more diffuse. The only difference is that they result from highly radial merger events that come in on orbits with low angular momentum. Okay. So in this study, we're using results from the spectroscopic and photometric landscape of Andromeda's stellar halo survey. So this is currently the largest spectroscopic survey of Andromeda to date. Here I'm showing the footprint of the survey. I'd also like to mention just the value of studying the Andromeda galaxy. So it's located 780 kiloparsecs away, which is over 2.5 million light years, which is at the edge of the local group. What that means is it's currently the only other Milky Way-like galaxy that we can study at the level, or even approaching the level of detail that's currently possible in the Milky Way. We can resolve individual stars within this galaxy, which means we can really study it in exquisite detail while also benefiting from this global external perspective. So the SPLASH survey is done with the DEIMOS spectrograph on the Keck telescopes and involves over 20,000 observations of individual red giant branch stars. In M31, we're obtaining spectra. So it's over 50 pointings. Each pointing is a 1-hour exposure, so it spans the stellar halo. It includes the tidal features as well as the dwarf galaxies in Andromeda and the disk. But here again, I'm talking about the tidal features. So in each pointing, we can observe hundreds of stars simultaneously. So what type of information do we get from our observations? Well, we know the positions of the stars on the sky. And from the spectra, we can obtain line of sight velocities. We also have information about the colors of the stars, which are related to their chemical composition. So here is a zoomed in image of the central few degrees of Andromeda. You can see the central disk region. And these rectangles in this zoomed in plot are representing the DEIMOS fields on the sky. So this is the location of our data. So within the SPLASH survey, we've targeted the system of tidal features that you can hopefully see within this image. We have the giant stellar stream in the south, which is targeted by the green rectangles and is that overdensity in the bottom part of this plot. But there's also this diffuse shell system. So some of them are outlined by the black dots in this image, and the one I circled corresponds to the northeast shelf of M31. So despite the fact that this feature was discovered in the early 2000s, it's evaded spectroscopic characterization until now. So we were not actually certain that it was a tidal shell for this reason. And this feature is particularly important to constrain the nature of the merger event that produced it, because much of the central debris from this event is predicted to be deposited in the region of the northeast shelf. So what does a tidal shell look like? It looks like Andromeda's northeast shelf. So here I have the relationship between the velocity along the line of sight, which has been shifted to the systemic velocity of M31, which is negative 300 kilometers per second, as a function of the projected radius from Andromeda's center. So the red giant branch stars located in the northeast shelf are the orange and red points here. The X's are Milky Way stars that are just intervening in the foreground along the line of sight. So hopefully what stands out to you is this very clear wedge-like feature. So this is basically an indisputable signature of a tidal shell. We know this from simulations. So this is a highly symmetric event as a consequence of the fact that it comes in on this radial orbit. So when you look at this in 3D space, meaning the 3D radial velocity and the 3D radius, a system of tidal shells looks like parabolas in this particular space. But when you look at it in projection, which means you only have the stars' positions on the sky and then the velocity along the line of sight, what you instead get is this triangular shaped feature. And that is precisely what we're seeing here. We also have some information concerning the geometry of this feature. We know it's located in front of M31, which means we know which component of the tidal shell is moving away from Andromeda, so it's outbound and then moving back toward us. So what you're seeing here are stars on various orbits moving away from Andromeda, approaching their apocenter, their largest distance from the galaxy, and approaching the systemic velocity, which is 0 in this plot, and then turning around and returning. And that's in essence what a tidal shell is. So we've confirmed that this feature is indeed a tidal shell, but it's a separate question if it's related to M31's last significant merger. So we think that this merger also produced its giant stellar stream, and again, these other shell-like features that I showed in that earlier plot. So here I'm showing just a roadmap of a simulation of this event, highlighting the giant stellar stream, or GSS, the west shelf, the northeast shelf, and the southeast shelf, with the location of our data overlaid on the model as these different colored rectangles. So we can compare the predictions for the debris pattern from the model to our actual observed data. That's the plot on the right here. And we're looking at the same space again, line of sight velocity versus the projected radius from Andromeda's center. So these red points are the satellite debris model. So this model was actually fitted only to data in the giant stellar stream. It has no knowledge of the data in the northeast shelf. And despite that, you can see that qualitatively it provides a very good match. And this is something that we have also shown statistically. So this provides fairly compelling evidence that these two events are related and that they come from the same original galaxy that was disrupted, likely within the last few billion years. One thing that's also exciting about this study is it's a first look at a multiple shell system. So spectroscopy for individual stars is something that we can really only do within the local group. There are many disk galaxies in the local volume, but given the techniques we currently have available and the instruments we have available, we can't do this type of work yet. So this is really a first look at a multiple shell system in any galaxy. So I'm showing the northeast shelf relationship between velocity and radius again, but we have data in these other features, as I said. We can look at the west shelf, which you can see here makes the same triangular shaped feature, and we can also look at the southeast shelf. So they form these concentric sort of nested wedge pattern. This is strong evidence, independent of any models, that these features are related. Because what you're looking at is basically successive orbital wraps of a single galaxy. So it's coming toward M31, and then as it's being tidally disrupted, you have material that is located closer into the galaxy as it loses energy. So it would be highly unlikely, that you had multiple processes that resulted in what we're looking at here. So the simplest explanation is that they have a common origin in this last significant merger. We also have evidence from looking at the chemical composition of these features. I won't show the plots in the interest of time, but we do find that they have very similar heavy element content, and that the distribution of their chemical composition also looks very similar, which provides, again, independent evidence of any models. So before I end, I'd just like to emphasize the value of studying Andromeda within the next 10 years. So as I mentioned, it's really our current best complement to the Milky Way. And in that sense, it really enhances our understanding of galaxy formation in the universe. So for this reason, Andromeda will really provide a foundation of interpretation for future observations of the local volume. It currently, straddles the regime between the local group and the local volume, which we'll be able to access in terms of individual stars with extremely large telescopes, and also study photometrically with the Roman Space Telescope. And many of the techniques used to study disk galaxies in the local volume will be similar in terms of using moderate resolution spectrographs. So hopefully we can study some of those in the future and study their tidal remnants and learn more about, galaxy accretion history and dark matter distributions that way. Thank you.
So we should be good for you to go ahead and start.
Okay, thanks, Susanna.
Yeah.
Hi, everyone. I'm Jacob Hamer. I'm a fifth-year graduate student at Johns Hopkins University doing work with Kevin Schlafman. I'm going to talk to you today about how
the audio is a little soft.
Oh, how about now?
That's better. And if you can speak close to your mic, we'll work on
Sure.
that.
Thanks. Hi, everyone. I'm Jacob Hamer. I'm a fifth-year graduate student at Johns Hopkins University. I work with Kevin Schlafman, and I'm going to talk to you today about how, using data from the Gaia satellite, we're able to address one of the oldest questions in the field of exoplanets, the origin of the hot Jupiters. So I'd like to start by showing you the solar system. The solar system has a very distinct architecture. You have the rocky inner planets closer to the sun, and then further away from the sun, you have the gas giants and the ice giants. And additionally, all of the planets in the solar system have their orbits closely aligned to the equator of the sun. That is, the planets' orbits are closely aligned to the rotation of the sun. And so all of this came together to give astronomers a pretty distinct idea for how planet formation occurred. But then on October 6, 1995, two very important things happened that allowed me to be here today. First of all, I was born. And second of all, the first exoplanet around a sun-like star was discovered, and it was called 51 Peg B, which I've placed on this plot, which shows the orbital period of the planets versus their mass. And 51 Peg B immediately stands out from the solar system planets. It's unlike anything in our solar system. It orbits 20 times closer to its star than Earth is to the sun, and orbits in just around 4 days. The proximity to its host star means that these planets are very hot, and so they were called hot Jupiters. And since then, we've discovered many hundreds. But the discovery of the first one immediately raised two really massive questions that have remained unanswered for decades. First of all, how does such a planet form when we don't have anything like it in our solar system? And second of all, what is the fate of such a planet that is so close to its host star? Can they survive? So as I said, the solar system planets orbit close to the equator of the sun, closely aligned. And we have been able to measure this angle for hot Jupiters as well. And while we have found that some hot Jupiters are aligned, just like the solar system and just like the hot Jupiter I'm showing you on the left, we've also seen that many hot Jupiters are misaligned from the rotation of their host stars. And so it may be that this is a big clue as to how they form. It may be that aligned hot Jupiters form through one process and misaligned hot Jupiters form in a different way. But we can't rule out the possibility that all hot Jupiters form misaligned and then later, over time, through interactions with their stars, become realigned. So if this were true, we would be able to study the ages of the systems in order to figure out if it's really happening. Because if you were to select a sample of misaligned hot Jupiters on the left and a sample of aligned hot Jupiters on the right, you would find that the aligned hot Jupiters are older because it would have taken them time to get there. And so if hot Jupiters form to be misaligned and get realigned over time, we would expect that aligned systems should be older than misaligned systems. And it was very difficult to answer this question because measuring the age of an individual star very precisely is one of the hardest problems in astrophysics. But using data from the Gaia satellite, which coincidentally has had its third data release today, we're able to use a new method to compare the relative ages of different populations of stars using how they move through the galaxy to inform how old we think they are relative to each other. And so on this plot, on the horizontal axis, there's a parameter that describes how similarly different stars are moving through the galaxy. On the left, stars move more similarly, those are younger stars. And on the right, stars move more differently, and they're older. And so younger things are on the left. And I'm showing here in these curves, different samples of stars hosting hot Jupiters. In orange, I'm showing misaligned hot Jupiter systems, and in blue, I'm showing the aligned hot Jupiter systems. And so remember that I said that if these planets are being realigned over time, then we would expect that the aligned systems would be older. Instead, we find that misaligned systems are older. And so we think that there's only one explanation for this observation. Misaligned hot Jupiters arrive on their orbits late, and aligned hot Jupiters arrive on their orbits early. And so this diagram is describing what I mean. The age of the system is increasing from left to right. And on the left, in the middle panel, I'm showing you how we think one way hot Jupiters may form. Planets form from the disk of gas and dust that surround their stars. And so we think that aligned hot Jupiters form within that disk and are able to migrate into their present locations before the disk disappears, which happens very early in a system's lifetime. Or it may be that they form in their present locations. But when the disk dissipates, you have a hot Jupiter aligned with its host star's rotation. In the top panel, I'm showing how we think misaligned hot Jupiters may form. They still form within the disk, but they form further out and they can't arrive before the disk disappears. And then a significant amount of time later, after some interaction with other planets or a companion star, the hot Jupiter is on an eccentric orbit, meaning it's not circular, and it's inclined, meaning it's misaligned. And soon after, interactions between the planet and the star allow the hot Jupiter to arrive on its small, circular, misaligned orbit. And so what this tells us is that there's not a single way that hot Jupiters form. They actually have multiple formation processes. And the ones that form aligned hot Jupiters tend to form them quickly and early, and the ones that form misaligned hot Jupiters tend to form them late, long after the disk has dissipated. So I'm just gonna leave you with some conclusions. We found that hot Jupiters form in multiple ways, with aligned systems forming quickly and misaligned systems forming later. I get into more detail in the paper, but we also do find some evidence that in some misaligned systems, realignment can occur, and you can form some aligned hot Jupiters much later on. And I just want to note that in 2019, I used the same method for comparing the ages of stars to show that the stars hosting hot Jupiters are younger than similar stars without hot Jupiters. And the only explanation for that observation was that hot Jupiters in-spiral into their host stars and are destroyed. Thank you.
Great, thanks so much. And Ricardo, if you just want to start sharing your screen, you should be able to take over.
Okay, can you see that and can you hear me?
Yes.
Great. I'm Ricardo Yarza. I'm a third-year grad student in astronomy at UC Santa Cruz, working with Professor Enrique Ramirez-Ruiz. And today I will talk about the intersection of fluid dynamics and the engulfment of planets by their stars. My contact information is in this slide, but it's also going to be on every slide. And I also want to highlight the important role that my collaborators have played in bringing this work to completion. I want to start by introducing planetary engulfment and sharing why it's so exciting. If you think of our solar system and specifically of the sun, most sun-like stars that are fusing hydrogen at their cores will eventually run out of it. And that triggers a whole different stage of stellar evolution. And what's important for planetary engulfment is that during that stage, the star expands significantly. And many of these stars will expand enough that they will consume their planets. So they will be larger than the orbits of their planets, and their planets will enter the stars. And that's something that we know for sure is going to happen in our own solar system for Mercury and Venus. But in fact, people who have taken the existing architectures of planetary systems and evolved them in time have predicted that a significant fraction of planetary systems will experience engulfment, meaning that at least one planet in that solar system will be consumed by its host star. And engulfment is also interesting from the observational side in that it might help explain some puzzling observations. The first of which is observations of giant stars that are rotating abnormally quickly. And the way you can think, or the way I think about engulfment sometimes is to think of the star as a cup of coffee and of the planet as a spoon. And once you put the spoon inside the coffee and you start stirring it, you're obviously making the coffee rotate. So once the planet enters the star, it's kind of stirring it up from the inside. And there's a population of giant stars that have been found to rotate very quickly. And one of the possible explanations is that they engulf the planet and the planets stir them up from the inside. So another explanation that is related to planetary engulfment is a population of giant stars that is rich in lithium. And that observation is unusual because lithium is very, very easy to burn. So most star-like objects will have very little lithium left at this stage of their evolution. But there is a population of giant stars that have abnormal levels of lithium and even more lithium than they're thought to have been born with. And a possible explanation is that they engulf a planet or a brown dwarf, since those objects are not massive enough to fuse lithium in particular planets. And the third observational clue that engulfment might be common is that people have observed planets and brown dwarfs are in close orbits around white dwarfs. And one of the possibilities is that, going back to the coffee cup analogy, if you stir the coffee cup hard enough with the spoon, some of the coffee is going to spill out. And in the planet case, if you have a massive enough planet or brown dwarf, you can stir up the star enough that its outer layers will be ejected. And you end up with a planet or brown dwarf orbiting what's left at the center. And this might help explain observations of these objects, planets and brown dwarfs, around white dwarfs. I will now motivate the method that we use to study planetary engulfment in the work that I'm presenting. The main challenge of modeling planetary engulfment that we're trying to address is that planets and giant stars are very different in size. When the stars become giant, they can be as large as about 100 solar radii, whereas the size of a planet is about 0.1 solar radii, like a Jupiter-sized planet. And if you try to do a single simulation of this process, it's very, very difficult, because it's like trying to take a picture of a landscape. And if you have a camera, you can take a high resolution picture of the landscape. But if you zoom in into, say, a tree, and you try to make out the details of that tree, it's going to be really hard because it's going to be pixelated. You took the picture of the whole landscape, but if you try to look at something that is very small with respect to that landscape, it's going to be very hard to look at its details. And something similar happens in planetary engulfment. If you try to run a simulation of the whole star, it's very difficult to accurately capture what is going on around the planet, because the planet is so much smaller. And so what we're doing here, or the approach that we took, is that we perform simulations of the zoomed in picture. So in the diagram above, it would be running a simulation of just the right half. And that's the physical environment in the vicinity of the planet. So it's as if you took your camera and you or binoculars and looked at the tree. you can now see every detail of the tree, and you're not looking at the whole landscape. So you're missing out on something, but that allows you to understand the features of the tree, or the features in this case of what the gas looks around the planet. So just to recap, what we did was taking planetary engulfment, which is a complex process that occurs at multiple scales and is depicted on the left half. And we zoom in and just look at what the physical environment around the planet looks like and what it can tell us about engulfment. And now I will discuss some of our results. The first is that the rate at which the planet is depositing energy into the star is different than you would expect from performing pen and paper calculations. And you can see that in the plot on the right, which is showing the energy deposition rate. So the energy per unit time that the planet is depositing into the star as a function of your position along the star. And the dashed and solid lines correspond to what you would expect from pen and paper calculations and what we actually observed in our simulations. And in some cases, those differences can be as large as a factor of maybe 10. And that energy deposition rate is very important because it allows you to make estimates about what's the effect that engulfment has on the structure of the star, or what's the luminosity that you would expect to see from this process. And that's what we looked at next. We found, using a very simplified model for how the energy is transported inside the star, that engulfment can significantly increase the luminosity of a star for up to a few thousand years. And the plot on the right is showing the luminosity as a function of time for a star that engulfs planets of different masses. And you can see on the y-axis that the increased luminosity can be a factor of up to maybe 10,000 from what it was before engulfment. So these are events that can drastically increase the luminosity of a star for a short period of time. Finally, we combined our results with semi-analytical estimates to try to determine what the outcome of engulfment was. We know that some planets, especially smaller ones, once they go into a star, they will most likely be destroyed. They will not survive that process. And one of the questions is, well, what planets can and what planets cannot survive? And that's what we are trying to determine on the plot on the right. This plot is showing the known exoplanets from the NASA Exoplanet Archive as a function of their orbital separation from their host stars on the x-axis and their mass on the y-axis in units of the Jupiter mass. And using our simulations, we were able to estimate that very massive brown dwarfs can actually deposit enough energy to eject the outer layers of the star and potentially survive the engulfment process. There's a lot of assumptions that go into whether the planet can survive, or how the internal structure of the star actually evolves during engulfment, because we're not explicitly modeling that. We're doing the zoomed in simulations of what the flow looks like around the planet. But one of the main results or outcomes of this work is a numerical framework that allows you to understand the vicinity of the planet. And that can be useful for doing estimates, as I discussed in these results here, and also to inform future work that tries to model in more detail the internal structure of the star. So do the zoomed out picture of engulfment. Here's a summary slide with everything I discussed, and it also has my contact information at the bottom and a link to the publication, which is currently under general review. Thank you.
Great, thank you so much. So I'm going to go ahead and put us into gallery view like this, I guess. I think this is probably the best we can do here. So thank you to all of our speakers. Those were really great presentations, and thank you for being so flexible with our slight technical difficulties. I think we've got things running smoothly now. So we're going to go ahead and move into a Q&A session now. So for those of you who are watching online, please send your questions in via the Q&A box that you see in the virtual platform. When you do so, please make sure to identify yourself and who you write for. And also those of you in the audience, please do the same. And can you also please identify who the question is intended for? So we've got Haley here who has a microphone and will wander around the room. Any questions? Ethan.
Hi, I'm Ethan Siegel of Starts with a Bang. My first question is for Jeonghee. Cassiopeia A was a type 2b supernova. You gave the motivation for studying this dust, or produced by it, as this will help us understand where the dust in the early universe came from. So this isn't clear to me. Can you tell us, what do we think we can learn about the dust produced by population 3 supernovae by studying a late, massive, metal-rich, evolved, hydrogen-stripped core collapse supernova?
Thank you. Yeah, so between those steps, we have a lot of models. We have to see how much metal produced from nuclear synthesis from the stars and how much dust each type. We have enough, explosion models to predict those things. So we have to project that case A particular, local supernova remnant, young supernova remnant, then project to in the early universe. Those I didn't, it's complicated, so I didn't show the those steps, but we use the initial mass function, how the stars born, as a function of the progenitor mass. So this is, also a good point. We have one data point with a lot of models involved, but we really need more samples. We can do this, especially really far infrared sky is complicated. So many material. I mean, I showed no dust in previous paper, but that indicate, it's no one is that stupid, but it showed that how complicated this title is to be able to find the dust directly forming in the supernovae. So unfortunately, it really polarization really shining new light. And unfortunately, Sophia, NASA decided to terminate Sophia. So I'm very disappointed. Our community is very disappointed by that.
Great. Govert?
I'm Govert Schilling, freelancer from the Netherlands, with a question for Ricardo. You said when a red giant is engulfing a planet, it can increase the luminosity of the star for a couple of thousands of years. I was wondering, how large is this luminosity increase, and will the start of it be very quick or very slow? And do we have any observational evidence of stars that are unusually bright that might hint at a recent engulfment of a planet?
This increase in luminosity can be very large. I think in the plot I showed, it went up to a factor of like 10,000, but it's relatively short compared to astronomical timescales. So the time it takes for a star to burn its hydrogen is 40 giga-year, and we found that the increase in luminosity can be at most something like a few thousand years. So I think it would be hard for it to be detected just based on how transient it is. Yeah. I think there was another part of your question. Can you remind me?
Yeah, I think I was wondering whether there are any observational evidence of this process, like stars that are unusually bright that you wouldn't expect that might be the result of an engulfment?
Not that I know of.
Great. Carrie, do you want to take some of the online questions?
All right, I have a couple questions here from Bill Waller of the Galactic Inquirer and Doc Waller's Earth and Space Reports YouTube series. The first question here is from Angela, or sorry, for Angela. You don't have to ask the questions. Does crystallization of volatiles such as water to ice also lead to the same sort of heating?
Yes. Do I need to say more?
Very succinct, thank you. Second question is to Jeonghee. How do supernovae compare with red giant stellar winds in terms of the amount of cosmic dust they produce?
AGB star, I mean, those stars are, the known source before supernovae. So it's create, in local universe, in our current universe, it's dominant dust. However, in early universe, they have not, were not quite sufficiently born yet. So because it's, a few million years since the Big Bang. So those first stars, population 3 stars, are very massive. So instead of low mass stars, which is taking a long time to evolve and born, and supernova quickly made as a first star, then explosion. So that's the time really cosmic dust is born. As Angela was explaining how important this is for the star formation in later on, whole history of the universe is different depending on how, how much dust we see at the early universe. So this is very important.
Hi, this is Ethan from Starts with a Bang again. This question's for Ivanna. Ivanna, I want to ask you, can we draw conclusions as to whether the multiple shelves we're seeing around Andromeda are arising from the same satellite galaxy that's been cannibalized, or whether they're arising from different precursor galaxies?
Yeah, so that was one of the main conclusions, was that the simplest explanation is this one.
That one.
Okay.
Oh, sorry.
Okay, maybe I'll just talk at a weird angle. But yeah, that was one of the main conclusions of this study, was that because we observe the multiple different shells, it's likely from the same exact galaxy that was destroyed. If it was multiple galaxies, it would be less likely that you would see this nested pattern. So the nested pattern corresponds to a galaxy, coming in and then producing successive orbital wraps, and each wrap of the progenitor, as it's being destroyed, the tidal debris loses energy and is the tip of those wedges were each at closer in radii, going from 30 kpc to 25 to 18 kpc. So it would be much more complicated to explain that with multiple discrete events. One thing I did not mention is that the other shelves, the west and the southeast shelf, also agree very well with predictions of the giant stellar stream merger event. So if you do similar comparisons to models as the one I showed, they also exhibit fairly excellent agreement. So this is really, the northeast shelf is the final nail in the coffin. I would say that this system of tidal features is related. Yeah, so in terms of the outermost one, the northeast shelf, would be the one that formed first out of the shells, and then the west shelf would be second, and the southeast shelf last, and that follows the radial order of the features. But the giant stellar stream is really the first feature that would have been formed. Yeah.
Any further questions in the room or online? Okay, with that, we're ending a little bit late. Sorry about that. But please do come back and join us this afternoon at 2:15 p.m. We have magnetic fields and galaxies. Again, thank you so much to all of our presenters. Thanks to all of you for being here. Thanks to our sponsor, USRA, and thanks to all the PIOs who helped work with the presenters and get the press releases together. Really appreciate it. See you this afternoon.